Right, so let's pick up with the next set of proof rules, or actually one proof rule sort of form. So we're going to do consequence, which is about helping us simplify reasoning about Hoare logic. And we'll also do a new tactic called e-apply that makes a bunch of this reasoning a lot easier to do in practice. So the idea with the consequence rule is that Hoare triples, as we've seen them so far, are very precise. So we basically say, if we have a precondition P and some command C, then we end up with some postcondition Q. And then if we want to reason about the next step, we say, well, let's make Q the precondition of some other command, and then go on from there. And the thing that gets a bit complicated with some of these reasoning steps is that it's not always the case that the pre and post conditions of different commands sort of line up exactly. So we may want to relax or tighten those assertions in various ways to make the reasoning work. So, for example, in this example here, we can say that if we do the assignment rule in this case with the post condition x equals 3, then we get this substitution here. So this substitution here is equivalent to true, like in the next version, but it's not syntactically the same assertion because it's a substitution using a signed sub. And so that's awkward because then you have to sort of actually do the substitution and all those sorts of things, and so on. So what the consequence rules let you do is things like saying, well, we don't really need a precondition that's exactly the one that's implied by some other rule, but one that's equivalent to it. So, for example, here is a version of consequence that says if what you're trying to prove is P CQ, then it suffices to prove P prime CQ as long as you can show that P and P prime are equivalent. Right? In other words, if assertion P holds, P prime holds as well, and if P prime holds, P holds. So this is an if and only if thing. So this lets you sort of adjust, so to speak, the precondition to use some other assertion that's equivalent to the one that you're actually looking for. And that's sort of doing the full sort of spec of it. If you sort of take that into a slightly different direction, you can say, well, you basically can do the precondition in one direction, so this one, which is just an instance of this equivalence rule here. But you could also do the same thing on the other end as well, which is saying that if you can show that P C Q prime holds, and Q prime implies Q, then you've got P prime P C Q. So it means that you can use a particular rule that gives you some assertion Q prime, but then you can use just logical implication to turn that into the Q that you actually really want. Okay, so these rules are not adding, if you like, analysis power for the different constructs of the language, but they're making it easier for you to reason about things. So we can formalize those two rules. So this is the pre version and this is the post version. And the proofs are quite straightforward because they're just essentially a form of transitivity, if you like, in the proof. So for example, here we can say, in this example, the precondition here is essentially that every state satisfies this true precondition, right? But if you think about it, when you apply, if you say that the postcondition is that x has to be equal to 1, and the assignment is x becomes 1, if you do this condition calculation using the assignment rule, you're going to get a thing here that's going to substitute in 1 for x in this thing. So you're going to get 1 equals 1 if you simplified it all. But that assertion is not syntactically the same as this assertion. Okay, they're not the same. They're equivalent functions, I guess, but they're not the same function. And so just using the assign rule means you have to somehow show the equivalence here. Whereas with this consequence pre, you can say, well, I'm just going to use the, I'm going to basically turn this true into something that is going to satisfy the assignment rule. So if I go back to the thing and apply this one, you'll see that what I've now got up the top is that predicate that I've selected with the application of the tactic of the pre-rule. And so now this first sub-goal is going to be satisfied by the assignment rule very easily. And then I've got to prove that the thing I really care about, which is the true here, implies the thing that I've actually got, which is this substitution version, right? Because that's the other assumption of the pre-rule. So I can discharge this bit first, and then there's a little proof to just show that the implication holds. So that's just a matter of unfolding everything and then simplifying, and you get the 1 equals 1, which you'd expect. So this is a pretty standard sort of example. So you can see it in the comment up here that the assignment, just to make it clearer, rid of the green. The assignment rule essentially gives you this bit, right? But what you actually want is true x becomes 1, x equals 1. So you have to also prove this implication here. And it's the pre-rule that lets you sort of do this reasoning in 2 steps rather than only being able to do it for the assignment rule. Okay, so that's how the pre-rule works. There's sometimes it's convenient. We had the pre-rule and the post-rule. Sometimes it's convenient to sort of do both of them at the same time. So here you can see that the thing we want is PCQ, but the thing we can prove is P prime C Q prime. And so as long as we can show that P implies P prime and Q implies Q, Q prime implies Q, then we've got the thing. So this is just a combination of the pre and the post together, and you can see the proof is just using the pre and the post. So it's a very simple proof to do. Okay, so that's the consequence rule. And we'll use the consequence rule a bunch of times in the future proofs and things. So it's very useful. One form of the consequence rule is very useful for all sorts of different proofs when you're sort of doing reasoning about a chain of things. But there's one sort of issue with this which we'll deal with a new tactic, which is when you do this sort of proof up here, and we've had some examples in the past where when you apply this pre-rule, if we just try and apply it, we get an error that says it's unable to find an instance for the variable p prime. And this is because the pre-rule has to have an instance for this variable, but that variable's value is not determined solely by what's in the goal, right? Because we're reasoning backwards here. When we apply, it matches the conclusion of the rule with the goal. And when it does that, it gets the values of some of the variables in the pre-rule, but not all of them. And in this case, p prime is not specified. So the way we learned before about how to deal with this is to use a with clause to say, well, we know exactly what the p prime should be and spell it out in detail. So this works, but it's quite tedious because this with clause is quite long to write down, and it's also, it requires you to sort of manually work out what it should be so that the next step, which is the assign application here, works, right? So what you can actually do instead is you can say, well, I don't want to nail down exactly what P prime is at this point, but I want it to be sort of held as a variable, essentially, as a whole, and the rest of the proof is going to somehow determine what it should be. And in this case, the use of the Hoare assign rule here is enough to say what this P prime had to have been for this apply Hoare assign to work. So that's the sort of background behind the apply rule. So I'll show you the difference. So this is basically a similar proof, but you can see instead of doing apply with and the intermediate thing, we've done apply. It stands for sort of existential apply. So what does that do? Well, it does the apply, but you can see that the P prime that it introduced is in here as sort of a funny question mark variable. So it's like a variable to be named later in some sense. So it's a placeholder. You can think of it, I call it existential variables. But basically there is going to be a value for P prime that sits in these two places, but we don't know what it is yet in the proof. Okay, and the constraint that you have in this sort of thing is if you introduce one of these variables, by the time you get to the end of the proof, when you do the QED, you've got to have worked out what the value of that variable is by using other tactics and things like that. If you get to the end and there's still some existential variables not bound to a value, then there'll be an error saying you've still got some work to do. So let's have a look at what happens next. So the next step in the proof is to apply the assignment rule, and this is the goal, right? And we can see that when we apply the assignment rule to this thing, the assignment rule will say, well, it's an assignment, and we know what the Q is, and in the rule it says, well, the precondition has to be the postcondition with a substitution applied based on the assignment. So the assignment rule knows, for it to apply, it knows what the P prime has to be to make that work. So when you do the apply Hoare assign, you end up at the same state you ended up with before, and the P prime has gone because it's been resolved, if you like. So let's think about that again. So this step is the apply Hoare assign goal, right? So the value of P prime will be determined by applying the Hoare assign rule. And when it's done that, it will then put that value down here as well in the next goal. So when we look at the remaining goal here, we'll see that the value is here. This is the value that the P prime was determined. It had to be that value for the apply Hoare assign to work. Okay, and the variable's gone now because we know what its value is, so we're okay. And then we can use we can do the rest of the proof from that point onwards. So this apply is really useful because it basically means you're saying to the system, look, I know I haven't told you what the value of this variable is, but the remainder of the proof that I'm about to do will constrain the value of that variable sufficiently to tell you what the value should be. And in this particular proof, it saves quite a lot of bookkeeping and writing down, because you don't have to explicitly write down what the intermediate assertion is, because the system will work out what it has to be based on what happens after the apply. So I think you'll find that apply is pretty useful for this kind of proof, and if you find yourself sort of thinking, oh, I need to add a with clause to get this to work, try the apply version and see whether that gets you to where you want to go without you having to explicitly do the hard yards. So this is an example of what happens if you don't do that. So, or if you don't fully determine the variables. So in this particular case, you've got a theorem that says that Pxy holds for all x and y, and you also got another one that says that if we know Pxy, we know Qx, and what we've got to prove is Q42. So obviously this follows because we can apply HQ, right? But if I apply HQ, oops, typing right. If I apply HQ, I get an error because to apply HQ, I need to know the value of y. But because the goal here and here doesn't constrain y at all, the system doesn't know what to use for y. So one way to solve it would be to do a with clause and say, well, it doesn't actually matter, so we just pick 0 or something. Okay, but you can see in the proof that they've got, we do an E apply. So what that's done is it's worked backwards in this rule, and it said, well, I know x is 42 because that's what I had in my goal here, but I don't know what y is, so we'll just leave that unconstrained. Okay, and that's fine as it goes. But then if you think about what happens next, well, next is we want to apply HP because we know that Pxy holds for all these things. If I apply that, I get that goal disappears, but this sort of slightly confusing message comes up which says, well, there's a shelf, which is kind of the place where it puts the obligations, if you like, to resolve the values of the existential variables. So it essentially puts it in as a goal on this, on the side, and it's saying, well, I'm going to need to get a natural number to satisfy what y is. And there's nothing else here because for y, in this case, it could be any natural number. So all I've got to do is come up with a number. But this is not very descriptive, I guess. And as it points out here, there's different error messages for different versions. So that's the kind of error you'll get if you get to the end of a proof without resolving all the existential variables. So this is a slightly different issue in the Spirit theorem. So this is a similar theorem, except in this case we just know that there is a y such that P42y holds. It doesn't hold for all y's. And so there's a different issue that happens here where we try the E apply. So we've now got the y from here is still undecided. And if we do this, we can say, well, this will, if we destruct HP, that will tell us a value of y, of the value of y that will be the one that satisfies this. So we can do that, and this calls it y, just to be confused. And there's a lot of sort of extra notation coming in here, but the basic problem is that there's a dependence here between variables that is not going to work. So now I want to apply HP prime, and you get this horrible error. And the problem with the error is that it's not very easy to see what's going on. But basically this part cannot instantiate question mark y, so that's the existential variable that was introduced. And it's trying to instantiate it using the normal variable y, but because the normal variable was introduced after the existential, you're not allowed to do that. So that's what this is not in scope means, and it tells you in the rest of the message what things are in scope that you could use instead, potentially. So that's not very clear from the message, but it's you may see it occasionally. So the solution is that instead of doing the destruct after the apply, you do it beforehand. So that introduces the y variable first, and now when you do the apply, the y variable is in scope for the question mark y existential variable. So now the final apply does work. Okay, so that's just a couple of cases where you might see funny messages from things. Okay, so one more tactic that's related to this is sometimes you have a theorem like this one where you in the previous theorem, when we did this apply HP prime, the natural thing to do, so this is the same proof down here, the natural thing to do is to do an assumption at the end. So at this point, HP prime is the thing we want to use, and this, in theory, should match it. And when we say assumption, it should find it. But assumption doesn't actually work if there are existential variables in the goal. So you won't be able to do that. So it's trying to match exactly that thing, and there is no such thing up here that matches exactly this. So there's a version of assumption called e-assumption, which, similar to e-apply, is like assumption, but it handles existential variables as well. So you can just do e-assumption here instead of apply HP prime. So that's a couple of new tactics that you will probably find useful for these proofs, particularly e-apply, because when you're doing a lot of reasoning about assertions being threaded through code, you often have to come up with intermediate assertions that you kind of know what they are, but writing them down and spelling them all out in gory detail is annoying, so e-apply lets you do that. And that's particularly the case for the consequence rules. Okay, so we're now sort of in the middle here. We'll come back in the next part and talk about the rest of these proof rules.